Hi everyone, welcome to the first lecture of the Advanced Analytical Techniques in CM4242. I'm your lecturer, one of the two lecturers. I'm Dr. Fong Fan-Man, okay, or my friends call me Fan-Man Fong. Fong is my family name. I'm here because I like to give lectures and presentation in chemistry. So you can find me at this address. You can email me if you have any questions. I would love to do a live lecture with you, but due to the pandemic, it's a bit hard for us to go back to the LT without the mask. But I'll still see you in the smaller sessions that will have a face-to-face interaction. So the first part of my lecture is on electrophoresis, specifically on capillary electrophoresis. So we call it CE in short. And the following slides are thanks to the courtesy of my professor, Prof. Sam Lee, who is also my PhD advisor. Okay, so first up will be the references for this topic on CE. So we have 3 references, and this book on the top right you can get on Amazon. If not, you can also borrow from a science library at the university. So the main references, right, will be the one from Schmidt-Coplin on CE. This is quite recent in 2016 on the methods and protocol, right, by Springer. And the second one you can find out more about CE in tandem with the microchip CE. And this is from 2013, and this is very useful later part when Professor Lee teach you on the microchip. This is by Garcia et al. And the last one, which is CE-mass spectrometry, CE-MS. This is by Wiley in 2016, and this is also very important because after this CE, I'm going to teach you on the mass spectrometry. Right. So in general, the outline of CE is that these are the 4 main points, 5 main points I will talk about. First, I will do introduction, so the basic concept of this very good equipment called the capillary electrophoresis. What is the principle of separation? Why do we need to separate? The purpose and how to do it. Third point will be the instrumentations. When we talk about instruments in chemistry, does it have to be very big size or can it be very petite and small? The fourth part will be understanding the column technology. What are the different materials in terms of separation? These small molecules, why are they able to elute and run at different speed? And also the effect of the electrolyte systems. And the last part, we can speak about the miniaturized analytical systems. Like how small can the instrument go? And the purpose, right? What's the reason to make it so small? Any applications in our daily life, etc. So CE is really modern. I would say modern even though it has been invented some years ago. It's really modern because it's nothing even better than CE. We still use it today. So if you invent an instrument in science and today at this time you stop using it, and that's not considered that modern. So CE is a modern analytical technique, right, which is used to separate different species based on the differences in their electrophoretic mobilities, right, in a suitable medium inside a small capillary. As the word suggests, capillary is very tiny, right? So we have got the blood capillary, so it's very fine, and it's all about separation, running in different speeds. It's about the speed of movement. So essentially, why we need to separate these particles is that we want to know exactly what is inside our sample. Most of the sample we have in our daily life, being the tea, the coffee you drink, or the bubble tea, is a mixture. Very rarely we have pure substances around us. Even the water we drink, after we boil it, it is not pure water, hardly likely. The bottled water we drink from the market that we buy, they are not pure. So there are some elements there, could be ions, could be some kind of compounds inside. So we want to separate and understand what are the chemicals inside. For instance, you have your can of a soft drink, right? You want to see, oh, what are the sugars involved? Is it corn syrup? Is it starch? Is it glucose, fructose, right? They all taste sweet, but maybe some of our senses cannot detect it. So this is why we have this instrument. Also to know the amount, not just to qualify them for identification, but also quantification. Now the term electrophoretic, you can see from root word is electro. Electro means the use of electric field, the positive and negative terminal, and the effect as a function of an electron's movement, right, that causes the species to run, right, at different speed. And besides the charge, the mass, right, the size could also affect its movement at a different velocity. So the advantage, right, is really the C here, the CE, the capillary. Why we want to have a very fine medium for them to run is because of a better heat dissipation due to a larger surface to volume ratio. What do I mean by that? suppose, right, you have a very thick column, right? Okay, a very thick column. So let's just say I give you this. All right, this is not capillary. So you see the cross section here, right? It's very large, right? Which means that if the heat is essentially in the middle here, it's very hard for them to dissipate because it takes a longer time for it to diffuse, and pass through the outer side. But if you have a narrow bore, for instance, in this glass stirrer here, you see, your surface to the volume ratio is very high. So that means any bit of heat inside the middle of this column, right, can spread the heat out very easily. We do not want to allow the heat to stay inside or the movement of heat to saturate because, right, heat can also affect the movement. But as you know from here, we want the CE movement to just be affected and measured by the charges and the size, not other factors like heat. Now, there are some historical development of CE. So it started in 1981 here by Jorgensen and Lucas from Europe, and they have done some experimental and theoretical approach to how to improve the high resolution, right, in electrophoresis. Take note, at the point of time, there wasn't some kind of like really today's world the capillary. It was like a glass capillary. So the glass, but very fine capillary. But as you know, glass is very brittle, so it is not sustainable, right? Any careless mistake, you can just break it, then you can't do the experiment anymore. And moreover, your sample, sometimes you have money amount, you don't want to lose them, and you don't want the machine to break down. So luckily, 2 years later, in 1983, right, Heaton, right, is the Dutchman, so he had applied these gel techniques to capillary column, right? Gel, like jelly gel, right? So it won't break because it has the material property. It is not as fragile as glass. So invented something called the capillary gel electrophoresis, and we know it still today for the DNA separation. Now next we have the Terab et al. They talk about how do they separate, right, neutral compounds if it's not charged, right? So we have something called the micellar electrokinetic chromatography, right? Still used today, right? When you use the CE. And of course, we have other inventions. Cohen and Karger demonstrated a higher efficiency, faster speed of using small tubing in the CE gel electrophoresis. And of course, after that, the first uh, registered commercial CE instrument was built in 1989, right? Which means now they have a stable CE and it's out to the world. Companies and even research centers can use it, to have some form of very recognized and reproducible data to do some research. And after that, of course, people talk about commercial instrument is very big and bulky, right? How can you carry this into on-site analysis if you are going to analyze it in a jungle or the mountain, right? And if you carry the sample back to the lab, it's too long and you can't preserve in those conditions. So we have something called the microchip CE, and we cover it later on. Then in the 20th century, part of the 19th century, we have the sequencing of the human genome by the CE based on the DNA sequencer, right? And this article can read along. And the later part become we have such a higher voltage CE, about 300 kilovolts here, super fast and high resolution. Why super fast? You can tell from the voltage along. When you have a big potential difference, right? Of course, you can just pass something that's charged in a higher rate, right? Okay. So in general, there are different modes of CE, right? We can change the mode, yeah, in this field, and this is something you ought to know. So when you read papers, you see the CZE, right? CZE. So CE in general is just a CZE. The Z we just drop it because it's zone electrophoresis. Because most of the time we analyze charged species. However, if your sample we know that most of the particles are not charged, then we use something called the gel electrophoresis, and we talk about DNA molecules here, RNA. These are very large molecules and macromolecules. So we need to use a gel electrophoresis to run. If not, they're just stuck inside. You can't even move them. You can't separate them. The next part I talk about is the MEKC and MECC for neutral species, also very important. And next we have the CEC, which is for something that's highly nonpolar. For instance, you have linoleic acid and your stearic acid, in beef fats, those long chains of hydrocarbon, very nonpolar, right? We need to use the capillary electrochromatography. So next we have also the capillary isoelectric focusing, the CIEF, which is for Zeta ions. Zeta ions, for instance, exist like your amino acids, right? You have your carboxylic acid group and your amine group, and then you switch the H plus ions to become charged particle. And when you become Zeta ion, it become a bit problematic because right overall the charge is the same as before, right? But the charges are on different sides. So how does it affect the movement? Right? Lastly, we have the capillary electrophoresis, the CITP, which is for very small ions, tiny ions. Could be, for instance, your fluoride ions, and those in your first couple of periods in the periodic table. So just about these individual ions there. So all in all, you can see C is very versatile because we have different modes of separations available. But all of them, no matter how complex it sounded or the specific description of CE, you can count the fact that, right, it's based on a very simple principle. The basic capillary electrophoresis instrument comes from only four main parts here. You can see from a table that this diagram, you need, first of all, two buffer reservoir. The buffer means you have some electrolyte inside, right, and you pass your sample through this capillary, the second part, right, and of course you need to have this in a way a salt bridge, or here we put a high power voltage supply so you can complete the circuit, right. And here we have a detector where our eyes or even our monitor can see. So only four parts, right, and know the reason why. So if you see that, right, most of the C instrument has these four parts, you can also think that, where should we start to pull, right, the analyte? Is it from left to right, right? Let them run first and analyze it, or the other side here? Think a little bit more, but we'll go through later. So it's really the basic instrument, and I expect you to know how to draw it the simple way. Describe the label, the diagram, right? When you see this high power supply, you can think of also DC or AC, alternating current or direct current. And of course, we talk about how the higher voltage affects the movement, right? Being high efficiency. So, of course, all in all, we can still monitor and modify certain parts of this instrument to make it very low cost and make it very smaller. So let's drill down to a bit more complex drawing here of the basic components of the CE here. So this is on the right side. This is what we use in a teaching lab and experimental lab here. Batman Cooter, yeah, another brand. Don't sell for them, but just some brands you can know of Dionix. Yes, so in this buffer reservoir, we have, of course, the inner outlet. Inlet means, right, this is where you pull the liquid up, and then outlet is where you put your exhaust. Of course, there are some other tubes here where you have the waste, right? So this is where you sample there. Now, you need to have a PC control because, right, you need to have a conversion of the signal, right? Either from a intensity of the ray, right? Either from the fluorescent detector or the ultraviolet detector. These are different, so you need to use the right module to connect to the PC, and then we can visualize it in those graphs here. Just like when you learned last time in your Fourier transform infrared, right? You see graph, but behind the scenes actually lots of waves and detections. Okay, and here you have also another part which is a power supply to modify the setting. So sometimes if you want to change the high efficiency, you might just want to change the power supply. So what it means is that next time when you do a research using CE and you see that, hey, when you press a button, nothing comes up here, right? Most people suspect it's a sample, or I have not enough sample, or it wasn't being prepared properly. But think about it, could it be because the power supply is not enough, or it's not functioning, or there's a breakage of the capillary, or, right, the liquid in the reservoir is not high enough such that, right, I'm always just withdrawing air, right, or the detector or the BC control. So it's something you want to think about. Now, another term I want to introduce, and you need to know about C, is the electroosmotic flow, the EOF here. We always talk about EOF. So what is it? It's talk about the ionization of this SiO group, the silicon dioxide group, right, or the absorption of the ions from the buffer, causes it to give a negative charges. Remember in the capillary, right, what is inside here is hollow, but also not so hollow. So it's made of a copper tubings, right, very capillary, but inside here in the inner walls is actually silica. So silica means you have the copper wall, right? You have the Si, silicon, and attached to O, the oxygen here. And of course, in different pH, the H plus can, it's a labile proton, can detach or attach, depends on the pH there. And depending on this condition here, it causes attraction and absorption of the ions, right? So that's why we have some uncontrolled kind of movement of this these ions if it's very close to the walls of this capillary. So hence we also have something called the, the diffuse double layer, and in the next slide we'll see the diagram representation. Okay, but of course you see that because your stationary phase, right, in your SiO is fixed, is solid, right, and then your first layer is tightly bound to it because it's the proximity to the oxygen minus is so close, so it is got a fixed layer. But the second layer, is a bit mobile because it's a bit of flexibility for them to move and change. So we call this the mobile layer. Okay. Yes. So, and because when you have this mobile layer is being pushed, right, there's something called the electroosmotic flow, right? Naturally, terms like stern plane, right, steeping plane or shear plane, zeta potential, and next slide over here we'll speak about it. So, as we covered, right. So this is a charged ion, right? This is not the O minus. It's just maybe let's say a chloride ion. Okay, a chloride suspended inside the capillary, highly charged Cl minus. Now there are some positive cations. Let's just say it's maybe sodium. Okay, for instance. I mean, ignore the size for a while. Now what happens is naturally because of that Coulombic attraction, you have all the cations surrounding this anion. Okay, just anion. Right, and because of the electrostatic attractions here, the first layer becomes like very permanent. So we call this the stern layer. Right, so you see the charge is very high on the surface potential. But the thing is, when the first layer is becoming more positive, it will attract what? Something a negative charge, right? So that's why you see some of these negative ions getting to attract it. And when you bring in negative charges, the positive charges comes along the way, right? So you see in the second zone here, we call the more between the stern layer and the shear plane, this part, right, second zone, this is where you have a mixture of the cations and anions, and this is very mobile, still moving, right? So here at the edge of the steeping plane, right, we call this the zeta potential. So you see that there will be some potential difference between the surface potential, right, to the zeta potential. Right? So we show that this ionic concentration, right, and this PD is really a function of the distance from the center, right, on the surface. Of course, center is relative to the perimeter of the surface of the charged ions in the medium here. So you can see that later on when we talk about the silica dioxide is the similar manner. Okay, so here you go, another diagram here. Imagine this is O minus of the silica in the inner walls of the capillary, right? So you have a diffusion layer, right, that will be mobile, and then the bulk solution where your ions are scanned through, there will be some incongruent flow. That means some will become they don't move naturally. They're affected by the existence of this stern plane and your electric double layer. Okay, so the zeta potential, right, we talk about this difference from the surface, the charge, is proportional to the thickness of double layer. So the thicker it is, right, your lower your zeta potential, and this is defined as zeta. Zeta is a Greek letter, is equals to 4 pi of the delta E over your epsilon. So epsilon is a dielectric constant. Is a constant called the relative permittivity, more of a physical chemistry physics side. The E is the charge per unit of the surface, and the delta is the thickness of the diffuse double layer. So in other words, right, your epsilon can also be defined as the ratio of the capacitance, right, something like called the electrical energy stored, right, of a material to that of a vacuum. So in vacuum, the reference point is 1. You can store more charges in your water, and methanol is on the scale of 30. Why water has a higher number here? Think of the HOH, the delta plus delta minus here, because your difference in electronegativity between the hydrogen and oxygen here allows them to hold the different charges in all the atoms, compared to the methanol where there's some CH3, carbon, hydrogen, the bonds are not so polarized. So the epsilon, you can also consider another equation, which is the C over C vacuum. It's just a ratio of the capacitance in the relative to the vacuum and air.